Bismillah ar-Rahman. Just quickly, last time we did like a minor mistake, so we can just try it again, because we said that if I have a T1 connection, the cost will be the reference bandwidth, which is 10 to the power 8, divided by the bandwidth of the T1 connection, which is a 1544, right? But we have to pay attention to the fact that the bandwidth of the link has to be in bits per second. That's another minor difference with EIGRP. If you remember, for EIGRP, we put the bandwidth in the metric calculation in kilobits per second. These are minor details you have to pay attention to, okay? But here, the bandwidth is in bits per second, so we have to do it like this. Okay, so for example, the bandwidth for EIGRP is 10 to the power 7 divided by 1544 multiplied by 256. If you go back, this is how you calculate. Okay, so that's a minor correction to the cost calculation that we did last time. So another very important difference that we need to pay attention to, as we said before, for when we discussed EIGRP, we said that conceptually bandwidth is a bottleneck parameter, right? So if we want to calculate the bandwidth part of the cost for an end-to-end path, what do we do? For an end-to-end path, we select the link with the lowest bandwidth, okay? And then we calculate the bandwidth. For the case of EIGRP, again, if you don't remember, if I have, let's see, if I have a path like this, wait a minute, how do I do that? Okay. So if I have a path like this, okay, and the bandwidth here, let's say the bandwidth here in kilobits per second, 1544, and here is 56, and here is 1544 in kilobits per second, okay? For EIGRP, so the metric for EIGRP, and I will calculate here the bandwidth part only, is for the end-to-end path is 10 to the power 7 divided by the lowest bandwidth, which is 56, multiplied by 256 plus the delay part. Okay. So this is the metric for the case of EIGRP. That's it. So you do not accumulate. So for the end-to-end path, the metric is calculated based on the lowest bandwidth. In that case, the lowest bandwidth is this. For the case of OSPF, the bandwidth is 10 to the power 8 divided by 1544000 plus 10 to the power 8 divided by 56000 plus 10 to the power 8 divided by 1544000. So that's how so this is how you calculate the cost. It's accumulated. unlike EIGRP. Okay, so why? Why do they do it this way for the case of OSPF? What happens is that if you have two paths, one with one hub and the other one with like 10 hubs, okay, one with one hub, which is let's say like this example, for example, this example here. If I have another path that looks like this, 56. That's it. Okay? If we use the bottleneck concept, the cost for those two paths is the same. The cost is the same. Right? Because this is 56 and this is 56. So the lowest bandwidth here is 56. And the bandwidth of this path is 56. So from the perspective of the bottleneck calculation, those are the same. However, those are definitely not the same, right? Okay? So I would prefer one over the other. So so that's why we use the accumulated calculation for the case of OSPF. Particularly because for OSPF, we don't have any delay calculation. Because remember, for EIGRP, it takes care of this already. By doing what? By using the accumulated delay, because the delay is accumulated. So it will take into consideration the difference between these two paths. However, OSPF uses only the bandwidth. So the only way that we take care of the difference between those two paths is by accumulating the cost. So you can consider that OSPF uses a combination of bandwidth and number of hubs, or the length of the path. That's in other words how OSPF calculates the path. Okay? So because the OSPF does not take into consideration the bandwidth, which is calculated based on accumulated delay. But here the delay. Here there's no delay. So the only way I differentiate between these two paths is by accumulating the cost of each link. So you combine the number of hubs with the calculation of the delay. This is the reason. Okay? So for OSPF, we use only the bandwidth. For EIGRP, we use both bandwidth and delay, plus reliability and load if we need to include those. So going back, to this slide summarizes what we have discussed into the fact that the cost for OSPF is the accumulated value, not using the bottleneck, which uses the minimum bandwidth across the end-to-end path, like the case of EIGRP. And why EIGRP does not do that is because the delay takes care of this. The delay part is accumulated already. So the delay takes care of this. But for OSPF, there is no delay. So we have to use another accumulated component. And what they have chosen here is the fact that we calculate the cost based on the bandwidth, and then you accumulate the cost for all the links. Okay? So for example, the the cost of this link is 64. So if R1 needs to go to this LAN, the cost will be 65 plus 1, which is what we have here in the routing table. So in the routing table we have 65. If we have EIGRP and the cost is calculated like this, then we take only the 64 and then we calculate the delay part of it, okay, which is a significant difference between the two. Okay? Any question? So this is the normal reaction when you accumulate the material too much. So you just lose track of what has been said before. So you just you have some difficulty in following. But I hope if you have any difficulty here, just point it out. Okay. So the way we calculate. So if we need to go to this LAN, we can go through this path or through this path. So we calculate the cost on each link, and then we calculate the total cost by accumulating the cost of each link. If the two costs, if one has lower cost, then this is the best path. If the two costs have the same value, what do we do? What do we do if the two paths have the same cost? Huh? What are the possible? Hey, this is the distance. This is the cost. This is the total cost. This path has a cost of 65, and this path has a cost of 65. Let's assume. What do we do? Huh? Choose anyone. No. The number of hops, the cost, the bandwidth, the delay, takes care. So it turns out that the two paths have the same cost. Okay. So if you go back to the material, you will recognize what should we do in that case. I will just leave it until you go back to the material, and I will bring it in the exam. Okay. That one important aspect is that for the case of OSPF, the bandwidth cost is accumulated. Another thing is that, as we notice here, the bandwidth on this link is 64 kilobits per second. This is the actual bandwidth. This is the actual bandwidth. However, this link is a T1 link. So how does this happen? Well, if you have a connection to a service provider, okay, the connection uses physical T1 cable, right? So the default bandwidth for that T1 cable is 1.544 megabits per second. This is the default bandwidth for the T1 connection. However, the service provider gives you only 1/4 of this. Okay? Or it gives you part of this. So the actual bandwidth that the service provider gives you is actually 64 kilobits per second. However, this link can physically carry a data rate of, in total, 1.544 kilobits per second. Okay? So in that case, if the link has two bandwidths, one actual and one fixed based on the physical characteristics of the link, what does OSPF use? This is the question here. Okay? So OSPF, does it actually take into consideration the physical bandwidth or the actual bandwidth? Well, the actual bandwidth is not known to OSPF. So OSPF, by default, even though the actual bandwidth on this link is 64 kilobits per second, but what will happen is that OSPF will take the fixed bandwidth of 1.544 kilobits per second as in calculating the cost. However, so this is the default. The default is that, so even though we have here 64 kilobits per second, but if we look if we say show interface and we look at the bandwidth, we notice that the bandwidth is a 1544 kilobits per second. It's not 64. So this indicates that OSPF takes into consideration the physical bandwidth of the link by default. Okay? So how do we let OSPF know that the actual bandwidth is 64? You have to do that manually. Okay, so the default is that OSPF will take into consideration the 1.5. As long as you say this is a T1 connection, it takes 1.544 megabits per second. So if you want to change this and take into consideration the actual bandwidth, then you have to configure that. So you have to go physically to R1, connect on R1 router, and then perform a command to change the cost of this link. And instead of becoming 64, it becomes more than that. Because when the actual bandwidth is less, the total cost will go high. And this happens because, this physical link supports 1.5, but your share of the bandwidth is less than that. This is what the service provider gives you. It doesn't give you the full bandwidth of the link. Okay? So you have to do that manually. You have to configure the router and change the cost manually. So OSPF will not do that by default or automatically. Okay? Any questions? So that's another thing. The rest of the slides we have already discussed briefly, and this is just to explain that in more formalized way, more details. So we discussed the multi-access networks. We said that this network is what we call a non-broadcast multi-access network. Non-broadcast multi-access. Why? Because you have a physical star topology like this, okay, with a switch in the middle. This is a physical star topology. Why do I stress on physical star topology? In 455, in course 455, if you remember, we have discussed something called physical topology and logical topology, if you remember, okay? So this is the physical topology. Does anyone remember what is the logical topology of this kind of configuration?
A bus.
Huh? A bus if what's in the middle is a hub. So your answer is correct if what's in the middle is a hub. Because a hub is a broadcast device. But the switch here, star? Star, okay, if it's a star, then if I send information from one router, it will go to the root of the star, and then it will go to one router only.
We are talking bus.
Huh?
So we're talking bus.
هو logical topology means that if you send information from one router and I want to access another router, what is يعني do I reach that router directly, or I have to reach it through يعني مثلا multi hubs and so on and so forth. يعني in other words, let's look at router 1. Router 2 is a neighbor to router 1 from a logical perspective or not? يعني if I send information to router 1 to router 2, does the physical topology give me the facility that I can connect directly? Why? Why? The switch will prevent me from doing that? So if I want to go to router 2, I can access it directly. يعني if I want to send any information to router 2, I don't have to go through any other router. That's the question. I don't have to go to any other router. And no other router will receive this information. The switch will only send it to router 1. Which means that router 1 and router 2 are logically connected like this. Logically. If I want to send to router 2, I will send to router 2. If I want to send to router 3, I will do the same. And if I want to send to 4, and if I want to send to 5, the same thing. Same here. 2 can send to 3, 2 can send to 4, 2 can send to 5. And 4 can send to 3, 4 can send to 5. So it's like what do we call this? A full mesh topology. A full mesh topology. So this configuration gives you a logical full mesh topology, which means that basically any router is a neighbor to all other routers. And this was the problem, because if I want to send link state advertisement, I have to send it here and here and here and here. And everyone has to do the same. If you remember, we discussed that last time. This creates a lot of overhead, a lot of communication, because you have to replicate the link state advertisement so many times, as you can see here. So there will be a big bottleneck on the switch from the physical perspective, because we have to replicate this on every link in order to reach all the other routers. So the most difficult thing is to use flooding or broadcasting information on a physically non-broadcast network. You know, if what's in the middle is a hub, the problem will not happen. Why? Because it's a shared link. So you don't have to physically send many packets to many routers. You see? You just send one packet, it will go to the shared link, and everybody will be able to read it. So if I want from any router to send to all other routers, I can send one packet only. But here, the switch has to replicate it. Right? So I have to, from the source, I have to send duplicate packets. I have to. Because this is a non-broadcast network. If it's a broadcast network, I can send only one. Because it's a shared link, everybody will be able to listen to it. Because if this is a hub, this is again a physical star topology. But the logical topology of a hub is what? It's shared medium. It's something like this. Right? Oh, sorry. Is a shared medium. So from any node, if you want to send to all other nodes, you just send one packet, and it reaches all. Because this is by default a broadcast network, but this is not a broadcast network. Okay? Any confusion? So based on that, using simple math كده, how many adjacencies do you have? How many links do you have? How many links, logical links, do you have in this topology? جبتيها منين؟ How did you get that?
Because everyone will have 4 links.
أيوة. And we have
5 contacts.
very good. Very close. However, your way of calculation counts both this, sorry, يعني it counts both this and this as two links. Okay? So what you have just said needs to be modified a little bit. We need to divide by 2. Okay? So again, so we have from R1 we need to connect to all other nodes. So for example, if we have n nodes, okay, we need each node needs to connect to n minus 1 nodes. صح? So in total we have n times n minus 1. However, this means that you have 2 adjacencies on the same link. So to resolve for that, we have to divide by 2. And this is valid for any number of routers. So any configuration like this, we convert it logically to this, and we can calculate the number of adjacencies based on this calculation. Very simple. So n times n minus 1 divided by 2. So for example, if you have like 10 routers, so it's 10 times 9 divided by 2. As simple as that. 45 links, 45 adjacencies. That's what any router will any routing protocol will recognize in terms of hello packets. So for the hello packets, it will discover that you have n minus 1 neighbors. So each node will discover n minus 1 neighbors because of this topology. And this topology is the trickiest. So the problem now is that using the flooding mechanism for this type of networks will create so much overhead. And as we discussed last time, designated router. So what OSPF does, instead of creating n minus 1 nodes, we will create only 2 neighbors. And instead of each node having n minus 1 neighbors, no. Each node will have physically 1 designated router and 1 backup designated router. So instead of sending the link state advertisement to all the neighbors, they will send it only to those 2, and those 2 will then forward it to other nodes. So in that case, we can save lots of overhead. So the designated router and the backup designated router, they go through what we call a selection process. There is a selection process that gets used to nominate the designated router and the backup designated router. So we will not go through the details of how you select that, but it's based roughly كده يعني it's based on the concept of a priority. So one router will have an interface with the upper مثلا IP address, with the highest IP address in the group. So it will have the highest priority. So this will be nominated as the designated router, and the one with the second best priority will have the role of backup designated router. Why do we have 2? Because if the backup router dies, or it gets dead, or it gets disconnected for some reason, then the whole network will be non-functional. So in that case, the backup designated router will overtake the job of the designated router, not to cause any interrupt to the operation of the network. So to send the link state advertisement, so this is the link state advertisement. To send it each node, instead of sending to all of them at once, they will send to all the DR others. DR others here, this means that all the other routers other than the designated and the backup designated routers. So for example, for this network, this is the DR, this is the BDR, and this is and those three are they call it DR others. DR others. So each one in the DR others router set will use a multicast transmission to send only to two routers, and instead of sending to all routers, they will send only to two routers. Okay, and they use for that IP address 224.0.0.6. This is the multicast address that they use, and this will send the link state advertisement to the DR and PDR, and then the DR or the PDR, they will forward this link state advertisement to the other links. Okay, any questions here? So this is to mitigate the issue of the high overhead by using all routers as neighbors and use all the adjacencies, which will create. Okay. No. This is initiated from the BDR. This is initiated from the BDR in case the DR is down. Okay, so this is BDR is sending to the DR others in case the designated router is down. Okay, really high. So the DR. Sure.
The previous slide, the DR sends also the LSA to BDR when the packet is forwarded to the other routers.
They will use another multicast address which only sends to DR others, not to the BDR. In the graph? Okay. So the election process, as we said before, occur in point-to-point, does not occur in point-to-point networks, because we said that for point-to-point is like for serial, two routers are connected through serial physical link. So in that case, the problem actually does not exist. The problem of flooding, the problem of very high overhead does not actually exist. So in that case, you don't need any designated router and backup designated. They are only two routers, right? So each one is neighbor to the other one, and that's it. What we need to do that for is when we have a non-broadcast multi-access network. So for example, this network is you have like serial point-to-point, serial point-to-point, and serial point-to-point, and here you have broadcast network, and broadcast network. So the problem here does not exist. The problem of flooding does not exist because none of these is actually a non-broadcast multi-access network. Okay? Anyone cannot recognize that from the topology? It's we don't have a switch like a physical star, and the star in the middle has a switch. This is what we call a non-broadcast multi-access network, and that's when the issue of high overhead in terms of flooding really occurs. So for this type of networks, you don't need to have any designated router or backup designated router. Okay? So, oh, this is the end. This is the end. Oh, that's it. Okay. Yeah, so that's it. So, let's